let's get ready for the second talk. We will have Lorenz on stage pretty soon. He is a fellow German, very much working with Bevy and known for a couple of traits that he's maintaining. And one of my personal favorites, a 2D particle system accelerated by GPU instancing. And I think we might hear a bit of that today in his presentation, because in order to do this, he had to dive into the rendering pipeline of Bevy. So I'm super excited. I never had a chance to do this myself very much yet. So I'm definitely going to learn something today. Lorenz, welcome.
Thank you for having me. Yeah,
here are your slides.
We started with rendering and we are going to continue with rendering, but now we are going to look into the pipeline of Bevy. Some sentences about me. I'm Lorenz, aka Lomix. I'm just a hobby game dev. I'm not a maintainer. And as Stefan said, I made a particle system and I'm really interested in the rendering works of Bevy. So before we start with looking into Bevy, we have to do some groundwork. We have to look how the GPU actually sees the world and what it does expect from us, the developer, to display stuff on the screen. So the very first thing, vertex or vertices. These are just points in 3D space. We pass those points in 3D space to our GPU, and then we say how they are connected to triangles, for example. Finally, these triangles are then projected into 2D space, and then for each pixel that is visible in 2D space, the fragment stage is called, and we have an image. Okay, we start with our vertices, indices, and instances. Those are the first steps in our rendering. We pass these points to our GPU. These are called the vertices. As mentioned earlier, these are just points, 3D positions in 3D space, followed by the indices. Since, okay, I have to, yeah. How do I start? How do I say it? Okay. When we render something like a cube visible on screen right now, these points, these vertices, are used multiple times. So for example, the middle one is connected to 3 other ones. Since we want to tell our GPU these connections, but we do not want to pass these points in 3D space multiple times. That's where the indices comes in. So first we pass in the list of the points, and then we pass in a big array of indices that describe the order in which these vertices are connected. And finally, we have the instances. This just describes how often the same vertex is drawn. This just probably makes no sense right now, but we will look into it later. And finally, the next step is the UV mapping. How do we get a picture on those triangles? For this, for each vertex, we pass a 2D value between 0 and 1 on X and Y. And these describe a position on a 2D plane. And this 2D plane is usually a texture. That's how we get the data on it. And this whole process, we do not have to do ourselves. We just define the points of each vertex. And then the GPU will calculate it for each pixel, and we can access it in the final fragment stage where we draw the texture. These steps in between are called the rasterization process from the GPU, when we go from the vertex stage to the fragment stage, and we don't have to care about that. Usually the GPU does it for us. And the whole process of this is called a pipeline, so describing which data goes in, how this data is laid out in memory, and how the GPU should interpret this is called a pipeline, so the whole configuration part. Also, yeah, on the screen right now you can see the different stages. We first start with the vertex input, which usually consists of our instance data, our vertex data, and our index data, and everything else we want to bind per index or per instance, followed by the interpretation in form of the shader code, and then our superglobals that are accessible to each stage if we define so. These are called the uniform buffers. Usually there goes our textures. And finally, the whole configuration part, how the GPU should interpret these data. So how does it look like in Bevy? First things first, There are actually two worlds in Bevy. When you create a game in Bevy, you usually have your systems running in the so-called app world. And in parallel to the app world, there's another world you do not have access to right from the get-go unless you specify so, and that's called the render world. The render world will typically sync in a special schedule, the extract schedule, together with the app world. And there, all the data from the app world that we want to render will be copied over to the render world. And there it will be further processed to finally being rendered. The most important resource in this render world is the so-called render graph. This is describing the whole order in which the Bevy will render each different aspect of our world. For example, the 2D part, the UI part, the 3D part, the post-processing parts, and everything else that goes into, like Bloom. Each of these things are a node on the render graph, and the render graph's main purpose is to bring order to these things, so everything is displayed the way you want it to be. For example, you usually want to have your eye at the very last stage, because it should be an overlay over your actually render world. These nodes on the tree just implement the node trait, and the most important function on this trait is the run function. And there, every node is given access to the render graph context, which holds the previous and next inputs and outputs together with the render context. This is the connection to the GPU, and of course, an access, read-only access to the render world. This is where we copied our data to. So, inserting a pipeline. Now, we want to create a custom pipeline, of course. How do we insert it into this whole structure? Usually, we don't want to create our own node unless we want to do something very specific. Usually, we want to extend an existing render phase to make something draw on the screen that works well with the rest of the screen. For example, when you have a sprite and you have something custom you want to draw, and the sprite pipeline doesn't give you access to that. For example, you want to have a spline. Spline renderer is not part of Bevy. You want to implement that, but you want to make sure that your splines are still in order. So when a sprite with a higher C index is drawn on top, it should be under this sprite. So we have to make sure that our pipeline is running in the correct order. And by this, we are adding it to the right path. In our example, we will look at the transparent 2D render phase. And that is basically the one that is, I'm missing the right word for that. It's the one render path that deals with all the sprites and material 2Ds. And the way it works, the main path, the node on the main path 2D, which will render all these sprites before bloom is happening or tone mapping, will query each camera or view that is currently active. And for each camera, each view, there will be another component on the render world, the render phase component. And this render phase component will hold a bunch of items, the so-called phase items. And each of these phase items describe an entity, they hold a reference to an entity, literally, that will be drawn on the screen. And together with this entity the phase item holds, there is also a link or a reference to the used pipeline to render this item and the draw command that is necessary, as well as the sorting. So the phase item's main purpose is not only to know how it's drawn or how it's rendered and which pipeline to use, but also in which order. The whole render process happening in the render world works step by step. The first process we already covered is the extract step, where we copy the data from the render world, from the app world over to the render world. After we did that, we did determine for which camera these items are being rendered by calling the queue stage. In the queue stage, we get all our cameras or views and add the items that we extracted to the appropriated view render phase. After we have decided what to draw and add it to the appropriated camera, we start preparing the data, meaning we have our transforms, for example, and we have to make sure that these data objects are getting cast into a data format our GPU can use. That's called a buffer. And they usually have to be compatible with a C-style struct. And that's exactly what is happening in prepare. We are taking our data, do maybe some computation first, and then we're going to write it to the GPU buffer. And in the final stage, the draw call, we then tell our GPU, hey, we have a buffer. It's there in your memory. Take it, bind it, load the shaders, and start the actual draw call. Oh, I just talked, yeah. We just talked about the extract stage, right? And the Q stage, here's another image showing it exactly. We have multiple cameras usually, or maybe you have multiple cameras. And for each of these cameras, we have to decide, we have to add a face item that means an item that is to be drawn for this specific camera. And these face items hold a reference to the entity in the render world, as well as the pipeline, the sorting, and the actual draw command. And the preparation, here we see it again. We take the data that we already extracted from the app world, and we prepare it for the WGPU buffers by doing whatever we need to do to our data to make it work with the memories. Yeah. And then finally, we have a draw call, which is in Bevy's context a tuple derived of multiple draw steps. We set the active pipeline. We then bind our first piece of data to our shaders by, for example, in this example, the view bind group is the all the transforms and projection matrices of our cameras, for example. We bind that as a uniform buffer so we can access it in the shader, and then we bind the texture we want to use, and finally we fire the draw call. Now, let's look at an example and see it in action. This was a lot of work and not a lot of work, a lot of words and many information that is probably very confusing. So the best thing we can do is to look at an example to make it a little bit more clear. For this example, we choose a very, very simple sprite rendering. So we basically implement our own sprite rendering using the Bevy icon, and we apply a simple vertex animation to the final output, which just squashes the item. We start with creating the components that live in our app world that we then are going to extract into our render world. And this is just a simple component in this case that holds a reference to the image we want to render. And we are going to use Bevy implements or provides us with some very handy macros, the asBindGroup macro in this case, that makes it very easy to convert this type of data structure in a WGPU buffer that our GPU can use. So it makes our lives a lot easier as developers by taking away all the boilerplate. We can call a simple function on the struct, and it will just spit out a buffer that we can then use to send over to the GPU. There's also another macro, the shader type. If you ever, for those who ever used the material traits before, they probably know this trait. Together with the asBindGroup trait macro, you can use it to create, as said earlier, data structures that you can easily bind to the GPU and send over without much hassle. So the second component is our pipeline. This one does not live in the app world. This lives in the render world. We are going to add it to the render world, and it holds the bind group layouts. These are the information about the memory layout of each of our data structures we want to bind. In this case, the view layout holds the information about our current camera, our perspective into the render world. And the second one is the uniform layout. In this case, it holds our image. And the third is the reference to the shader we are going to use and run. And also together with our pipeline, we define our pipeline key. This is just something that we can use to access our pipeline, our cache pipeline later on in the shader process. And also you can bind some data to it. Usually it's used for some sampling configurations. But for now, we just keep it empty here. We just want to have it as a simple way to get our pipeline from the cache pipelines later on. So the mesh. Instead of using Bevy's built-in mesh, we're going to use our own because it's a very nice example and shows us how the buffers are working, how the vertex buffers are bound. So we are going to create a fixed quad mesh here that is a resource. This resource will be just loaded once because for our sprites, we always pretty much want to just render a quad and then bind the texture on that. It's not going to change. So we're going to create a resource and we're going to use two vectors to store our data. The vertex buffer holds the points that represents this quad. In this case, it's a point for each corner. And the index buffer holds the order in which the lines are connected between those. So we're going to implement the from world trait for this one because, as I said earlier, it will just be loaded to the GPU once. We don't have to modify it in any way, shape, or form. The values will be kept between 0 and 1, and we will stretch it later. So we are going to get the render device and the render queue. The render device resources in the Bevy render world is just the configuration of your current GPU hardware. And the queue will let us queue up commands that we are going to send. In this case, we are going to create the two buffer vectors, which are just regular vectors, but with the addition that we can bind them or send them over to the GPU. Makes it very easy again for us. And we are just going to make our quad mesh in form of 4 points and directly write it to the GPU. So the memory is now on the GPU. And we do the same with the indices. In this form, we have a list of 6 indices because each triangle is composed of 3 connections between 3 vertices and 3 lines. And the indices describe the index into the vertex buffer, so to say. So each vertex is just an array, and the index just is the list of, as the name implies, indices into that buffer to get the order right. So configuring the pipeline. Now that we have our data, we want to tell Bevy, or rather RepGPU, WGPU, how our pipeline is looking, how the connection is working, and how the interpretation of the data we are going to send is working. We already have our pipeline defined. We also implement the from world trait for our pipeline. We are going to get the render device again because we need the configuration of the actual hardware below. And then we are creating new bind groups for that, meaning we are telling WGPU, or our pipeline, better to say, how the data that we are going to send is going to look in memory. And the first one is the view layout, which consists of the view uniform and the globals uniform. These just hold the data from our camera. These are directly from the Bevy core. I didn't make my own. So there's the projection matrix and all the position of the camera and all the information that we are going to need to get the right angle on our 3D world later in the vertex shader. And also we are going to create the uniform layout. And now, since we implemented the as bind group macro on our structure, we can easily just call the bind group layout, pass our render device, and we just get the layout back from that. Makes it very easy. And of course, I haven't highlighted it, but we are going to load the shader from our asset server, which we got earlier, and pass it onto our pipeline resource that we then gonna add to our world. So next, we are going to implement the specialized render pipeline trait for our pipeline. This one will describe how this pipeline is going to work. And since the pipeline is, when this is called, the pipeline is already created. So the data we just prepared is already accessible to us. We have a reference to self, and we're going to use that to create a new render pipeline describer. This one is directly from WGPU, just wrapped in some Bevy-specific stuff. This one will describe the whole working of the pipeline. And to that, the first thing we are going to do is we are binding our uniform buffer consisting of the view layout of our camera or view, and of course of our texture. Then we are going to find the vertex state. This will be the first entry point into our rendering. We are going to find the shader that this vertex state is going to use. We keep it very simple. We just define the function that it's going to call it. It's called the vertex, so we just leave it at that, and we are not passing any definitions or extras in there. The shader definitions can be used to bind specific information, like, for example, MI, WASM, or WebW, WebGPU, WebGL2, and then we can specify values for these specifics and then access in the shader to make some if conditions. For example, WebGL2 has a very specific requirements on the layout that they are probably aligned in a certain way. So we usually have to do some padding there for our values. And we can pass these, we can pass some Boolean values there and say, hey, you are WebGL2. Please add some padding here and there for the buffers, so they are probably aligned in memory. But we're not going to do that for this example. We just leave it empty. So now we are going to define the actually input data for our vertex state. And the very first one we are going to bind in the first slot is the information about the position of each of these vertex or vertices. And it's just a simple vec3. So we are going to say that the value just holds a single float 32 times 3, meaning a simple vec3. And we are going to tell our GPU how much byte that is in memory. And we say the most important part, we are setting the step mode to vertex, meaning that this value is bound to each vertex. The next vertex will probably have a different value for that, and that's kind of important. And together with this vertex buffer, we are going to bind our second vertex buffer, and this one is not specific to the vertex, but to the instance. And meaning that each vertex of one model will share this information, and this information consists of the actual transform of our sprite in form of the translation, rotation, and scale. Also in vec4 format, we will construct a transformation matrix from that on the GPU and multiply it to set it in the right location later on. After the vertex state is defined, we are defining the fragment state. The fragment state will just we will just pass. It's mostly happening on the GPU. We already know what we are going to get, because what we are going to get, we will going to define on our vertex shader. And all we have to say here is we link the shader we are going to use, and we specify the target. In this case, the target is an image of a specific format. That's the Bevy default texture format. Usually, you would also add, since we are extending the mesh-to-D pipeline here, you would probably create a copy of the mesh-to-D pipeline in the from world constructor of your pipeline and load this kind of information directly on the pipeline you're extending. And if you don't, you have to do it yourself. And if you fail at that, the program will crash. Same goes, the next step is the primitive state. Here we will define how the GPU will interpret the data going in. And the most important part here is the topology, where we tell the GPU that the array of indices we are sending represent a triangle, meaning three consecutive, three indices in the row construct a triangle. There's also different kind of ways to interpret. We can basically make a line, for example, but the triangle is the most common one. And also the font phrase, we are just going to ignore that for here for our example, because we don't need it. But the font phrase define in which order the indices go. So if they go counterclockwise, we are looking at the front side, and if they go counterclockwise, we are looking at the back side of a mesh. This is important for the cal mode, so we can remove stuff we don't see anyway, but it's not important for the example. So we're gonna leave it at the default. And the very last part is the multi-sampling. Here we define how many samples we are going to take from the image. And also, this is usually something you would load from a preloaded pipeline. In this case, as mentioned, the mesh-to-D pipeline, because it's set to 4. And since the path is running all on the same, it is required that these have the same values. So make a mistake here and the whole program fails. But we didn't do that because I wanted to show how it's done in general. After our pipeline is then described, we go over to run it. So back to the different schedules of the render world. The first thing we are going to do is we're going to extract our data from the app world. And for that, we are just going to create a simple system. And the data that we want to use in the render world, in this case, the extracted sprite instance, which holds our transformation matrix and the C ordering. So we know if it's, and the C ordering. In this case, the C ordering just consists of the C position of our transform. And we are going to create a new special variable, the sprite transform matrix, that will hold our transformation matrix in pod style, as we are using the byte mu crate here to make this struct compatible with C style structs. Pod just stands for plain old data, so it's a very simple type of data that the GPU can handle, and it makes it very easy for us to bind it later to the GPU buffer. So we are going to query the app world, and since we are currently running in the render world, we have to wrap our query in the extract struct. So the Bevy knows that we are actually accessing the app world. We are going to get the global transform and our custom sprite together with the view visibility. And then we are just going to iterate over all our entities, check, are they visible? If not, we just continue. And else if they are, we create the components we just created for our render world and just copy the entity over and insert these components into it, and the rest is empty. So the queue. The next step is the queue. Here we want to get all our views or all our cameras, and we want to add for each camera that has that can see our entity, we want it to the render phase of this entity. So we're just going to get the get all our pipeline information. We're going to get the render phase from all our views together with the visibility of the visible all entities of these views and our extracted data. We're then going to get our draw function from our cache, and then we're going to iterate over each camera view. And for each camera view, we create a new specialized pipeline. And then we are going to go over each of our entities we just extracted, check is this entity visible in the current camera. And if so, we are going to add the so-called face item to the camera face, meaning, hey, you are going to get rendered by this camera. And we pass the entity, the pipeline, the draw function we want to use, the batch range. We are not using the batch range, but it's just something of the transparent to the pipeline phase that determines how often this thing is drawn. After it's queued, it's time to prepare our data. So the queue phase, after the queue phase, we are going to access our data again and prepare it for the GPU. Meaning we are going again with our data, extracting it from the render world, and together with all the information that our GPU needs to bind data. We then iterate over all our extracted sprites and transform the appropriated buffers we want to have. The first one is the instance buffer that holds our transform data. We're just going to create a draw from a buffer describer. It's also a web WGPU thing that will hold our data. And then we are going to create the uniform buffer. Again, since we implemented the as-bind group layout, the as-bind group macro here, we can simply call a function that is very ready to use for us. We are just passing our layout information, our render device, the image, the render assets, meaning the GPU images and the fallback, and then finally, we're going to insert a new struct into our render world, into the entity, and that is the prepared version of our extracted data in form of the uniform buffer and the instance buffer. So finally, we enter the final stage of the draw. Since the main path of the render graph from the node to the render path will proceed to call the render command for each face item. We define the draw command as a tuple consisting of each of the steps necessary to bind the data and draw it to the screen. So on the first step, we are just readying the pipeline by saying you are active now. Then we are binding, we are calling a built-in function from Bevy, a part of the mesh2d pipeline. We are just telling, this is just a simple function that will bind the already extracted few parameters of our camera to our data, to our pipeline. And of course, this is also happening inside of Bevy. We don't have to do it ourselves. That's, yeah. And then we bind our uniform data in form of our texture, and finally our draw call. Let's look. Let's go into the steps and look exactly what is happening here. The first one is the bind group. Here we implement the render command for a struct we defined, the set bind group struct. And this just has a generic implementing a constant, and this constant stands for the grouping we are going to use. In this case, it's group 0, standing for our texture. And we are going to implement the render command. The render command is implemented on a face item, and or 4 face items, better to say, and is called then by our main2d path. And it will, we define the parameters. Since each face item holds an entity, we can define what data we want from that entity. For the entity, there's the item query, and we want to have access to the prepared data we prepared earlier, in this form, the prepared sprites. And we don't want any resources or information from the view. We just want to prepare data, and we're going to unwrap it, safe unwrap it, look if it's there on the entity, and if so, we are binding it to our render path, which means we are sending the first command. We say, hey, you have some data in your buffer. This one is relevant, bind it to the next phase of our rendering. And then we do the final draw call. Here we get, this time, our mesh we already prepared in the very beginning in form of our resource, and also the prepared sprite again. We're just gonna unwrap this data since it's a Rust thing, and there are a lot of lifetimes in the way, we unwrap it into the inner part of that resource where we have access to the index buffer and the vertex buffer we defined at the very beginning. And we then just gonna tell the GPU, since it's already there, hey, you have some data there, please bind it to the appropriate slots for the next phase. And when all that has happened, we finally tell our GPU, okay, the data is bind, you have access to everything, it's finally time, draw something. And here, the first parameter, we just gonna pass 0 to 6, which means draw the first 6 vertices, followed by how often we are going to try the instances. And in this case, since we just have in this example just one instance, the sprite instant count is just 1, meaning draw the first 6 vertices once, basically. Now we are going to put this all together in our final plugin, where we define all these stages. So this is how it looks, where we are creating a new plugin. And the first thing we are going to do in our build step is we are going to need writable access to the render app, which is a sub app of our normal world. And to this render app, we register our new commands. First one is our draw command, and we want that on the transparent 2D face item. The face item, the transparent 2D is the implementation of a face item specified for the transparent, for the 2D space, for everything that is 2D and transparent, I guess. And we are going to initialize also the pipeline in form of our specialized render pipeline. Then we are going to add our extract system that we already covered, and then the different systems running in the render schedule. The first one is the queue, then the prepare one, and that's about it. The rendering is done on the render graph that we don't have to deal with here. And finally, our data in the finish function of our plugin, meaning when everything is loaded, since we usually want to have access to, for example, the mesh2d pipeline in this case, and access some of this configuration, we initialize our pipeline and our fixed mesh in the finish function. That's about it on the Bevy part. Finally, we are going to look on the GPU part, how to interpret this data. And for that, we have already created a shader. And the first one is, the first step is defining the input variables that we already bound. And in this case, in the first group is our view together with the globals. These come from the Bevy function, the Bevy render command function to bind a camera view that we used. And the second group is our texture. Then we define our vertex input. This is the data that we send over into the vertex state. And this just consists of our two buffers. The first one, the vertex buffer, holding the information about the point in 3D space. And then the instance buffer that is the same for all vertices of this model. And this is the transformation, rotation, and scale. The translation, rotation, and scale. And then we finally define the output. The output of our vertex state usually goes, well, it always goes into the fragment stage with then finally will cover each pixel, pixel by pixel. And for that, all we want to have is the clip position that we have to pass, so the rasterization stage knows which pixels are visible and which are not. And the UV coordinate, which represents a point for each vertex on a 2D plane, which then samples the final texture. Whew, that's a lot of words. Okay, the vertex stage. Here we take our vertex input, and the first thing we are going to do is we take the instance input for each vertex and compute a transform matrix. And that's this part here. We don't need to know how it's going to work. It's not important. Just know multiplying matrices usually results in a position in 3D space. That's all you have to know. And we are also reading the texture size because we didn't pass any information about the size of our quads. We just render a texture, and we want to have this texture the same size as, we want to have our final render product to be the same size as the texture we are passing in. So we're reading the texture size here. And then finally, we also going to create some sort of animation item. In this case, we are just going to take the sine wave of the time that is also passed with the view buffer, and make it positive, give it a minimum of 0.2. So our final quad looks like it's getting squashed. Then we define an offset. Since our mesh data is between 0 and 1, technically the center would be in the down left corner. And we want to make the center of the quad the center of the screen. So we're going to offset the position by half on each axis. Then finally, we compute the actual position from the perspective of the camera by taking our view projection, multiplying it by the instance transformation and the position of our vertex together with some multiplication of our animation scale on each size. So yeah, that is covered. And then finally, we are going to take, I forgot to highlight that, but finally we are going to create the view, the UV, and this is just the position of our vertex. In this case, since we defined them between 0 and 1, we are just going to pass the UV as the vertex data. All we have to do is inverse the y-axis, so our picture is not upside down. And this is all we are going to return. And then we are going to pass this to the fragment stage, and the fragment stage will just sample the texture given the UV coordinates we just passed. And this finally will result in an image. And this is basically all we have to do on the Bevy part. When we create an object, we are just spawning the spatial bundle, which just consists of the transform and visibility components, and then add our custom components with this byte to that. And that leaves us finally with a rendering of a sprite, of our own sprite pipeline, not using something from Bevy. And we are binding a texture and displaying a little vertex scaling animation on the y-axis. Ooh. Sorry, was a little bit rough, but that's about it. Yeah.
Lorenz, wow, what a intensive run through tons of code. I had no idea that it takes so much work to come up with a custom render pipeline.
It's strange. Yeah, it takes a lot of work just to display a texture. Yeah. Let's just displace the power of a rendering system in general, how much it abstracts away from the complexity of the whole thing.
Yeah. Lorenz, thank you so much for presenting this. I heard that a couple of people will use that as a reference because they are having a project to create a custom render pipeline at some point. So yeah, I'm happy to see that you've put this example also on GitHub so people can follow along and play around with the code and a working example.
Exactly. Yeah, I imagine that this is a little bit too much for talk. So at least I want to leave some sort of example that if you're interested in creating your own pipeline, you have something to start and maybe some information to have a rough understanding of the systems in place and why they are there.
Yeah, let's say I've seen a ton of questions. I would pick out the top one now, and we save the rest for the Q&A at the end. So how did you figure all of this Bevy specifics out? Did you read the code, or is there a good onboarding guide for the rendering?
There is, well, basically, Bevy is pretty much a very fast-moving engine. Every few months, we have many, many changes, especially in the rendering department. So most of the guides out there are usually, or information you find are usually either outdated or only cover half of the truth. So the reality is you have to really get into the engine part and just open the Bevy repository and look how they do stuff. There are tons of really, really cool tricks used there, especially in the sprite pipeline that is not common sense and not easy to understand unless you really dig into it.
But you would say it's it doesn't take a PhD to understand that code. It's well documented and
just some genuine curiosity.
Yeah,
that's all.
Well, that's encouraging because I guess your talk will also be outdated otherwise in a few months.
It will probably be, yeah.
Yeah. Lorenz, thank you again. A big hand from everyone in the stream for this presentation and a great onboarding guide for the rendering pipeline in Bevy. I'm gonna put you down stage now, and we're going to continue with the next presentation. We have to get going here. We are running out of time.
Oh yeah, sorry.